Hello and welcome. I'm so grateful you're here. As we begin, I'd love it if you'd share in the comments where you're joining from and what time it is for you. It always amazes me to see how people connect from every corner of the world, morning or night. Thank you kindly to those who've subscribed and pressed that little like button. It really does help. And if you ever have requests or themes you'd like me to explore, please share them in the comments. Now let's get started. Chapter 1. Cosmic Dust, the Building Blocks of Stars. In the vast canvas of the universe, cosmic dust and gas float like whispers of creation. This faint, shimmering matter, composed mostly of tiny particles, plays an essential role in the grand narrative of the cosmos. Imagine particles so small that they dance through the vacuum of space, barely detectable, yet profoundly influential. These tiny grains, reminiscent of the finest sand on Earth, are the building blocks from which stars, planets, and even life itself emerge. Cosmic dust is not just an afterthought in the expanse of the universe. It is a crucial ingredient in the recipe for creation. Formed from the remnants of ancient stars that have exploded in magnificent supernovae, this dust contains elements forged in the heart of those celestial giants. Carbon, oxygen, silicon, and iron, elements we are familiar with, are mixed within this cosmic dust, waiting patiently for the right conditions to ignite the next chapter in the cosmic saga. As we look deeper into the cosmos, we encounter molecular clouds, vast regions of gas and dust where these particles coalesce. Picture these clouds as enormous ethereal blankets that stretch across the night sky, often obscuring the light from distant stars. Within these dense formations, the interplay of gravity and temperature creates a sanctuary for the seeds of stars. It's within these clouds that the magic of creation begins to unfold. The role of gravity in this process cannot be overstated. Gravity acts as the invisible hand that gathers and binds these particles together. Imagine a gentle yet persistent force, pulling the dust and gas closer, causing them to clump together over time. As these clumps grow larger, they begin to attract even more material, spiraling into a dance of accumulation that culminates in the birth of a star. This gravitational embrace is what transforms a disparate collection of particles into a cohesive unit, ready to ignite the fires of nuclear fusion. The conditions within a molecular cloud are critical for star formation. Temperature and density play pivotal roles in this intricate process. When a region of a cloud becomes dense enough, the gravitational forces become overwhelming, leading to an increase in pressure and temperature. Imagine the moment when the temperature reaches a tipping point, igniting a fusion reaction that causes a star to shine for the first time. It is a moment of triumph, a spark of light in the darkness, a beacon that signals the birth of a new celestial body. Renowned astrophysicist Carl Sagan once said, "The cosmos is within us. We are made of star stuff." This profound statement captures the essence of our connection to the universe. Each element in our bodies was once part of a star, forged in the crucible of stellar processes. The cosmic dust that gathers in molecular clouds is not merely matter. It is a legacy of ancient stars, a reminder of our origins. As we contemplate the birth of stars, we can imagine the sheer scale of these processes. Some molecular clouds can stretch for light years, containing enough material to create hundreds of thousands of stars. Within these vast regions, the interplay of forces creates pockets of density, each with the potential to ignite and become a new star. The universe is a place of constant creation, where the old gives way to the new, in an eternal cycle of life and death. The environment within these clouds can be hostile, with turbulence and shock waves altering the dynamics of star formation. When massive stars reach the end of their lives, they explode in supernovae, sending shock waves through surrounding clouds. These shock waves can compress regions of gas and dust, triggering the formation of new stars. It is a cosmic cycle of destruction and rebirth, where the remnants of the past fuel the creation of the future. Imagine the beauty of this process. Stars are not born in isolation. They often form in clusters, where multiple stars arise from the same molecular cloud. This clustering creates a dynamic environment, where young stars influence their neighbors, sharing energy and material. As these stars shine, they emit radiation that can heat and disperse the surrounding gas and dust, shaping the very landscape of the galaxy. The delicate balance of forces within these clouds is a testament to the complexity of the universe. The interplay of gravity, temperature, and pressure creates a symphony that orchestrates the birth of stars. Within this grand design, each molecular cloud serves as a cradle for new beginnings, nurturing the seeds of stars that will illuminate the cosmos for billions of years to come. As we explore this cosmic phenomenon, we are reminded of the wonder of our universe. The very dust that floats silently through space holds the secrets of creation, waiting for the moment when conditions align and a star can be born. Consider the enormity of what this means. Each star that lights up the night sky has a story, a history intertwined with the dust and gas that surrounded it. In contemplating the vastness of space, we are drawn into the mystery of our origins. The very elements that make up our bodies were once part of stars that lived and died long before our planet took shape. This connection to the cosmos is profound, reminding us that we are all part of something much larger than ourselves. The process of star formation is a reminder of the delicate balance within the universe. It is a dance of creation that continues to unfold, each moment a testament to the power of gravity and the beauty of cosmic dust. As we ponder these celestial processes, we realize that we are not mere observers. We are participants in an ongoing story, woven into the fabric of the universe itself. The next time you gaze up at the stars, consider the cosmic dust that brought them to life. Each flicker of light represents a journey that began in the depths of molecular clouds, propelled by gravity and ignited by the warmth of creation. The universe is alive with possibilities, and in its heart, the building blocks of stars await their moment to shine. In the heart of molecular clouds, the intricate dance of particles continues, guided by the relentless pull of gravity. As dust and gas accumulate, they create dense cores, regions where the weight of the material begins to compress under its own gravity. This process, often likened to the slow tightening of a fist around a handful of sand, leads to the formation of protostars, embryonic stars that hold the promise of future brilliance. Imagine a serene, glowing sphere of gas and dust slowly coalescing, its temperature rising as pressure mounts. Within this tiny fragment of the universe, forces are at play that are monumental in scale, yet delicate in execution. As the protostar grows, it begins to radiate energy, not yet from nuclear fusion, but from the gravitational energy released as material falls inward. This energy manifests as a soft glow, a precursor to the dazzling light that will one day shine forth. As a protostar evolves, it enters a critical phase marked by the onset of nuclear fusion. Within its core, hydrogen atoms are squeezed together with such intensity that they begin to merge, releasing energy in the form of light and heat. This transformative moment is akin to a gentle awakening, where the darkness of space is pierced by a new star's light. It's a reminder that even in the vast emptiness, life can emerge from the stillness. Consider how this process reflects the broader themes of creation in the universe. Stars are not merely isolated entities. They are part of a grander narrative that includes galaxies, nebulae, and the very fabric of space-time. The energy produced by stars fuels the cosmic cycles, influencing nearby stars and the molecular clouds from which they arise. This interconnectedness is reminiscent of a vast web, each thread vital to the integrity of the whole. The birth of a star is not without its challenges. As protostars form, they often encounter the remnants of their molecular clouds, which can stir turbulence and chaos. Shock waves from nearby supernovae or the gravitational influences of neighboring stars can disrupt the delicate balance, leading to variations in star formation rates and outcomes. Some stars may find themselves in crowded clusters, while others emerge in solitude. each shaped by the conditions of their birth. Within these stellar nurseries, we also find a variety of stellar types emerging. Massive stars, which burn brightly and live short lives, often evolve rapidly, creating spectacular supernovae that enrich their surroundings with heavy elements. These elements, forged in the fiery hearts of stars, contribute to the cosmic dust that will later form new stars and planets. In contrast, smaller stars, like our Sun, take their time, existing in a stable state for billions of years before they exhaust their fuel and transition into red giants, ultimately shedding their outer layers and leaving behind a white dwarf. This stellar evolution is a cosmic clock ticking away through eons, marking the birth and death of stars, each cycle contributing to the ongoing narrative of the universe. The remnants left behind after a star's life, whether in the form of supernova debris or the gentle drift of a planetary nebula, serve as the building blocks for future generations of stars and planets. As we ponder this cosmic ballet, we can reflect on the words of the renowned physicist Richard Feynman, who remarked, "The imagination of nature is far greater than the imagination of man." This sentiment rings true as we consider the unfathomable processes that govern star formation and evolution. The intricacies of these processes are beyond our complete understanding, yet they inspire awe and curiosity about the universe we inhabit. What might it be like to witness the birth of a star, to observe the swirling gas and dust coalesce into something magnificent? Imagine the colors of the nebulae, the vivid hues of blue and red as different elements interact and emit light. Each star born from these clouds carries with it the potential for worlds, perhaps even life, to emerge in the future. The conditions required for star formation are also affected by their environment. For instance, in regions where molecular clouds are dense and rich in material, stars may form in rapid succession, resulting in clusters of young stars that illuminate the surrounding darkness. These clusters can be seen across the night sky, their collective glow a testament to the synergy of creation. Yet, not all clouds favor star formation. Some remain quiescent, their dust and gas dispersed without igniting the fires of new stars. The interplay of external pressures, like the gravitational pull from nearby galaxies or the radiation from massive stars, can inhibit the accumulation of material, leading to regions of space that remain barren for ages. This variability in star formation is a reminder of the universe's complexity. It highlights the delicate balance of forces at play, and the myriad conditions that must align for creation to occur. Just as in our own lives, where moments of inspiration can be fleeting and rare, so too are the moments when stars ignite amidst the cosmic dust. As we continue to explore the universe, we become witnesses to this magnificent cycle. Each star that forms brings with it the potential for new planets, new systems, and perhaps new life. The cosmic dust that once drifted silently through the void transforms into vibrant stars, illuminating the darkness and inspiring generations to gaze upward in wonder. The next time you look at the night sky, consider the stories etched in the stars. They are not just points of light, they are symbols of resilience and rebirth. They remind us that from the smallest particles of dust, immense beauty and complexity can arise, echoing the fundamental truth of our existence. We are all part of this grand cosmic narrative, woven together through the very elements that once gathered in the darkness, waiting patiently to ignite the light. Chapter 2. Protostars, the birth of a star. In the heart of molecular clouds, where cosmic dust and gas converge, the story of stars begins anew. As we drift through this celestial nursery, we can almost feel the gentle embrace of gravity pulling the scattered particles together. When enough matter gathers, a remarkable transformation occurs. The gas, once merely a whisper in the cosmos, begins to collapse under its own weight. This process marks the birth of a protostar, a phase rich with potential and energy. As the gas collapses, the temperature and pressure within the core of the forming protostar rise dramatically. Imagine the immense forces at play, akin to squeezing a sponge filled with water. As the volume decreases, the energy becomes more concentrated. The gravitational energy released during this contraction transforms into thermal energy, heating the core to astonishing degrees. It is a cosmic furnace igniting in the dark, where the warmth begins to radiate, glowing faintly amid the surrounding darkness. This rise in temperature is not just a mere byproduct. It is essential for what is to come. The core of the protostar grows increasingly hot, reaching thousands of degrees. It is here that the dream of nuclear fusion begins to stir, like a sleeping giant slowly awakening. Fusion, the process that fuels stars, occurs when atoms collide with enough energy to overcome their natural repulsion. In the case of protostars, hydrogen atoms, the most abundant element in the universe, are poised to engage in this celestial dance, but not just yet. The conditions must be just right, and in the early stages of a protostar's life, this is still a distant promise. Surrounding the protostar, an accretion disk forms, a swirling mass of gas and dust that encircles the burgeoning star. Picture this disk as a cosmic carousel, spinning gracefully in the vastness of space. The material within the disk is drawn inexorably toward the protostar, feeding it like a mother nurturing her child. This accretion process is vital, as it not only fuels the protostar's growth, but also plays a crucial role in its eventual transformation into a fully fledged star. The significance of the accretion disk extends beyond mere sustenance. As the material spirals inward, it experiences friction, converting kinetic energy into heat. This heating further elevates the temperature of the core, hastening the journey toward nuclear fusion. It's a remarkable synergy, where the act of gathering matter ignites the very fire that will illuminate the cosmos. Throughout history, many have marveled at the process of star formation. The renowned astrophysicist Carl Sagan once said, "The cosmos is within us. We are made of star stuff." This profound connection reminds us that every element in our bodies was once forged in the heart of a star. It is fitting, then, that the journey of a star begins with the gathering of cosmic dust, leading to the formation of protostars. But why does this process matter? Why should we pause to reflect on the birth of a star? Understanding protostars is essential because they represent the very foundation of our universe. They are the building blocks of galaxies, solar systems, and ultimately life itself. The intricate dance of gravity, heat, and pressure in these early stages sets the stage for the diverse range of stars we observe today. Each protostar carries within it the potential to become a massive blue giant, a gentle yellow sun, or even a dim red dwarf. As the protostar continues to evolve, the temperature at its core climbs ever higher, inching closer to the threshold necessary for nuclear fusion. At this point, the protostar is teetering on the brink of a momentous change. Imagine a world where the very fabric of existence is about to shift. The core's temperature may rise to millions of degrees, and soon, hydrogen atoms will collide with enough force to fuse into helium. This moment, when fusion ignites, is the point at which a protostar transforms into a true star, illuminating the darkness of space with its radiant glow. As we reflect on this journey, we realize that each protostar is not merely a point in the cosmos. It is a unique story, a culmination of millions of years of cosmic evolution, waiting for the right moment to shine. The birth of a star is a reminder of the beauty inherent in the universe, of how from chaos and darkness can emerge light and life. In this vast celestial drama, we find ourselves drawn to the profound interconnectedness of it all. The elements forged in these early stars eventually find their way into planets, asteroids, and ultimately into the very fabric of life. It prompts us to consider the unbroken chain that links us to these distant wonders. Each protostar shines a light not only on the cosmos, but also on our place within it. So as we wander deeper into the realms of star formation, let us hold on to the imagery of these nascent stars cradled within their cosmic dust. Let us be gentle observers of this grand process, where energy and matter coalesce to form something greater than themselves. The universe, in its infinite wisdom, invites us to witness the birth of stars, a testament to the beauty and complexity of existence itself. The journey of a protostar is just beginning. Each moment is filled with potential, each flicker of heat a promise of what is to come. As we breathe in the enormity of this cosmic tale, we prepare ourselves for the next chapter, where the flicker of nuclear fusion will illuminate the vastness of space, giving birth to the stars we gaze upon in awe. As the protostar matures, the accretion disk continues to play a pivotal role in its transformation. This disk is not merely a passive collection of gas and dust. It is a dynamic environment where interactions shape the very fate of the forming star. Among the swirling materials, some particles collide, merging together in a cosmic ballet, while others are flung outward, unable to resist the gravitational pull of the central protostar. This ever-evolving disk holds secrets that will determine the characteristics of the star to come, including its mass and, consequently, its lifespan. The journey of a protostar through this phase is not uniform. It experiences fluctuations in temperature and pressure, creating a complex interplay of forces. As the core heats up, the surrounding materials begin to respond. Imagine the tension building within a tightly wound spring, ready to release energy at the slightest provocation. In this celestial arena, the protostar undergoes what is known as thermal pulsations, where bursts of heat may temporarily increase the energy output, sending ripples of change throughout the accretion disk. It is during these moments of heightened energy that the conditions for nuclear fusion inch closer to reality. The protostar is like a pot of water on the stove, simmering just below the boiling point. The pressure from the weight of the gas above compresses the core, while the rising temperature seeks to ignite the fusion reaction. This delicate balance is crucial. If the temperature reaches a critical threshold, the hydrogen nuclei will collide with such vigor that they will fuse into helium, releasing an immense amount of energy in the form of light and heat. This momentous shift does not happen in isolation. The formation of a protostar is often accompanied by the birth of a star cluster, where multiple stars emerge from the same molecular cloud. Picture a family of stars, each with its own destiny, yet bound together by the same cosmic lineage. The interactions among these nascent stars can influence their development. Gravitational forces may alter their paths, leading to unique outcomes. Some may become massive stars that burn brightly and briefly, while others may evolve into smaller, longer-lived suns, contributing to the diverse tapestry of stellar evolution. Throughout history, scientists have sought to understand this process. The work of pioneers like Subrahmanyan Chandrasekhar illuminated the path of stellar evolution. Chandrasekhar, who was awarded the Nobel Prize for his contributions, famously stated, "We must be prepared to get our hands dirty in the pursuit of knowledge." His insights into the balance of forces within stars highlighted the intricate dance of gravity and pressure that governs their formation and eventual fate. As we envision these protostars and their surrounding disks, we may wonder about the energy that lies within. What is the nature of this energy that fuels the birth of stars? The answer lies in the fundamental forces at play. Gravitational energy, released during the collapse of gas, is converted into thermal energy, driving the rise in temperature. As the core becomes hot enough, the potential for nuclear fusion emerges, unlocking a reservoir of energy that will sustain the star for billions of years. In the early stages of a protostar's life, the initiation of nuclear fusion is an exhilarating prospect, a cosmic promise waiting to be fulfilled. This process is not instantaneous. The pathway to fusion is fraught with challenges, as the protostar must contend with the balance of temperature and pressure. Yet, as the core's temperature continues to rise, the conditions will soon align. The fusion process marks the transition from a protostar to a true star, a moment that echoes through the cosmos, heralding the birth of a new celestial body. As the gravitational forces continue to compress the core, the fusion reactions will initiate. Imagine witnessing the first flicker of light in an otherwise dark room. The transformation is profound. The protostar will begin to emit radiation, illuminating its surroundings and signaling the dawn of its existence. This radiant energy will push against the gravitational forces, creating equilibrium that defines a stable star. The significance of this moment extends beyond the individual star. It contributes to the recycling of materials within the universe. The elements forged in the hearts of stars, those very same building blocks that formed from cosmic dust, will eventually be released back into space when the stars reach the end of their lives. This cycle of birth, death, and rebirth is the essence of cosmic evolution, shaping the universe as we know it. In this cosmic journey, we may reflect on the interconnectedness of all things. Each protostar, each star that takes shape, is a reflection of the universe's creativity. The energy and materials birthed from these stars will eventually give rise to planets, moons, and perhaps even life. The story of a single protostar is but a chapter in a much larger narrative, one that links us to the cosmos in ways we are only beginning to understand. As we continue to explore the intricate processes at play in the birth of stars, we invite you to pause and appreciate the beauty of this cosmic creation. Each protostar, with its swirling accretion disk and the promise of nuclear fusion, is a testament to the wonders of the universe. It reminds us that in the depths of darkness, there is always the potential for light. The birth of a star is a celebration of energy, matter, and the infinite possibilities that lie within the vast expanse of space. The journey of a protostar is a magnificent odyssey, a dance of atoms and energy that sets the stage for countless stories waiting to unfold. As we linger in this moment, we prepare to witness the incredible transformation that awaits, a wondrous spectacle where the protostar finally steps into the spotlight, igniting the cosmos with its brilliance. Chapter 3. Main Sequence Stars, the Stable Phase. In the grand narrative of the cosmos, main sequence stars emerge as the steadfast pillars of stability. These stars, with their luminous glow, serve as beacons in the night sky, illuminating the vastness around them. Imagine gazing up at a clear evening sky, where countless points of light twinkle, each representing a star in its prime, a main sequence star. Characterized by their relatively steady state, these stars burn brightly, fueled by the very essence of hydrogen fusion, a process that fuels their existence and dictates their lifespans. At the heart of a main sequence star lies a core, a furnace where hydrogen atoms collide and fuse to form helium. This nuclear fusion releases an immense amount of energy, radiating outward and illuminating the star's surface. Picture this process. Hydrogen nuclei, with their positive charges, are repelled by one another, yet when the temperatures soar high enough, these particles overcome their repulsion, merging into a new form. The energy released in this fusion reaction is nothing short of miraculous, creating the light and heat that travel across the cosmos to warm distant planets and illuminate our own world. Consider the balance at play in the life of a main sequence star. The energy produced in the core creates an outward pressure, pushing against the inward pull of gravity. This equilibrium allows the star to maintain a stable size for millions to billions of years, depending on its mass. Imagine a delicate balance, like a perfectly poised scale, where any shift could lead to dramatic consequences. The lifespans of these stars vary widely. More massive stars burn through their hydrogen quickly, living for only a few million years, while smaller stars can sustain their fusion for tens of billions of years, quietly shining in the cosmic darkness. The diversity of main sequence stars is as astounding as the cosmos itself. They come in various sizes, temperatures, and colors, each presenting a unique story. The spectrum of these stars ranges from the small, cool red dwarfs to the massive, blazing blue giants. Each type plays a vital role in the cosmic ecosystem. Red dwarfs, for instance, are the most abundant stars in the universe, their longevity allowing them to exist for trillions of years. This makes them historical witnesses to the unfolding of the cosmos, quietly observing events from a distance. In contrast, the blue giants, with their intense heat and brightness, live fast and die young. Their lifespans, mere blinks in the cosmic timeline, end in spectacular supernovae, scattering their elements across the universe, seeding new stars and planets. Among these stars, the Sun, a yellow dwarf, stands as a prime example of a main sequence star. It balances the forces of gravity and energy production in a delicate embrace, providing warmth and light to our planet. As the renowned astrophysicist Carl Sagan once said, "The cosmos is all that is, or ever was, or ever will be." Our Sun, a part of this magnificent cosmos, exemplifies the stability and brilliance of main sequence stars. As we reflect on these celestial bodies, it's fascinating to ask how these stars influence life on Earth. The Sun's energy sustains our ecosystems, drives weather patterns, and fuels the very processes that allow life to thrive. Imagining a world without the Sun invites a sense of wonder and gratitude for the sustaining force of main sequence stars. They are not merely distant points of light. They are the lifeblood of the universe, shaping the very fabric of existence. In the heart of every main sequence star, we find a microcosm of the universe itself. The processes of fusion and energy balance echo the larger themes of creation and destruction that govern the cosmos. As these stars burn, they transform hydrogen into helium, releasing energy that radiates into the universe, while also creating the conditions for future generations of stars and planets. This cycle of birth and rebirth is not merely a scientific observation, but a poetic reflection of the universe's ongoing story. From the smallest red dwarf to the most massive blue giant, main sequence stars showcase the incredible variety of stellar life. Each type of star represents a unique chapter in the cosmic tale, contributing to the great narrative of creation. As we gaze up at the night sky, we are reminded of the interconnectedness of all things, where each star plays a role in the grand design of the universe. The main sequence phase is not just a period of stability. It is a vibrant, life-sustaining chapter that bridges the quiet beginnings of a star's life with the spectacular ends that lie ahead. Within this intricate dance of energy and gravity, we find a deeper understanding of our place in the cosmos. It invites us to ponder how these celestial bodies influence our lives, how they represent a journey through time and space. As we explore the characteristics of main sequence stars, we begin to appreciate the delicate balance that sustains them and, by extension, us. The universe, in all its complexity, continues to unfold in ways both astonishing and beautiful, with main sequence stars shining brightly at its center. The characteristics of main sequence stars are as varied as the stars themselves. Each star, though bound by the same fundamental processes, exhibits a unique personality shaped by its mass, temperature, and composition. This diversity invites us to consider how these traits influence the behavior and life cycles of stars, revealing a rich cosmos of stellar phenomena. As we contemplate the energy production within these stars, the process of hydrogen fusion serves as a magnificent cornerstone. The immense gravitational pressure in a star's core generates temperatures that can soar to millions of degrees. Here, hydrogen nuclei collide with such force that they fuse, forming helium and releasing energy in the form of light and heat. Imagine this process as a symphony of atomic collisions, where each fusion reaction echoes with the promise of warmth that travels across the void. The energy released during fusion not only illuminates the star, but also creates the outward pressure that counters gravitational collapse. This interplay of forces maintains a delicate equilibrium, allowing the star to shine steadily for eons. It prompts us to ponder, how do these forces shape the very structure of our universe? The answer lies in the balance, the harmony of pressure and gravity, that governs the life of a main sequence star. The lifespan of these stars reveals fascinating insights into their nature. A star's mass is a key determinant of its longevity. While the smaller red dwarfs burn slowly and can last for trillions of years, the more massive stars exhaust their hydrogen fuel at a furious pace, living only for a few million years. This stark contrast raises intriguing questions about the fate of these celestial giants. What becomes of them when their fuel runs low? As we explore the various types of main sequence stars, we encounter an impressive spectrum. Red dwarfs, the most abundant type, are dim and cool, often appearing as faint flickering points of light in the night sky. They represent a remarkable tenacity, enduring lifetimes that far surpass their more luminous counterparts. In contrast, the yellow dwarfs, like our Sun, shine brightly, providing the necessary energy for life on Earth. Their balanced state allows them to flourish. Yet, like all stars, they too face an inevitable fate. Then we have the blue giants, radiant beacons of energy that burn with a ferocity unmatched by their smaller siblings. Their brilliance is captivating, yet their lives are fleeting. These stars, often several times the mass of our Sun, live fast and die young, culminating in spectacular supernovae that scatter their enriched materials across the galaxy. This process not only marks their end, but also paves the way for the birth of new stars and planets, perpetuating the cycle of creation. Among these stellar types, we find exceptional individuals that have left their mark on the cosmos. Consider the famous star Betelgeuse, a red supergiant that resides in the constellation Orion. Though not a main sequence star in the traditional sense, it once graced that phase before evolving into its current state. Betelgeuse is a testament to the life cycle of stars, showcasing the beauty of transformation. Its eventual supernova will be a cosmic event witnessed by generations to come, a reminder of the transient nature of existence. This leads us to ponder the interconnectedness of these stars within the grand scheme of the universe. Each main sequence star contributes to the cosmic narrative, influencing the formation of planetary systems and the evolution of galaxies. The elements forged in their cores become the building blocks of life, connecting the stars to the very essence of existence on Earth. The energy radiating from main sequence stars creates a tapestry of environments across the universe. Imagine distant worlds orbiting these luminous giants, where life may flourish under the warmth of a steady sun. The conditions for life, as we understand them, are intricately linked to the characteristics of the stars around which they orbit. The stability of a main sequence star creates a nurturing cradle for planets, fostering the conditions necessary for life to emerge. As we delve deeper into the lives of these celestial bodies, we can appreciate not only their beauty and complexity, but also the way they mirror the cycles of our own existence. The processes of fusion, balance, and transformation are reflected in the natural world, reminding us of our connection to the cosmos. Just as stars evolve and change, so too do we, participating in a grand cosmic dance that transcends time. In contemplating the significance of main sequence stars, we come to understand their role in shaping the universe. They are more than mere points of light. They are vital forces that drive cosmic evolution and sustain life. Each star tells a story, a narrative woven into the fabric of the universe, inviting us to listen and to reflect on our place within this vast expanse. In this exploration of main sequence stars, we find ourselves at the heart of a cosmic journey. From the birth of hydrogen fusion to the delicate balance of forces that sustain these stars, each element contributes to a larger understanding of our universe. As we gaze up at the night sky, may we carry with us the knowledge that these stars are not just distant entities. They are integral to the story of existence itself, illuminating the path of creation and discovery. The life of a main sequence star is a remarkable journey through time, characterized by its unique evolutionary path. Each type of star, from the humble red dwarf to the majestic blue giant, presents an extraordinary case study in stellar evolution. These differences not only highlight the diversity of the cosmos, but also reflect the vastness of possibilities that exist within it. As we envision the evolution of these stars, it is essential to recognize the role played by their mass. A star's mass determines not just its luminosity, but also its ultimate fate. Massive stars, like the blue giants, burn their fuel at an astonishing rate. Their cores, under immense gravitational pressure, reach temperatures that ignite nuclear fusion in a furious blaze. The energy they produce is so tremendous that it allows them to shine with a brilliance that can outshine entire galaxies. But this rapid consumption of hydrogen means that their time as main sequence stars is fleeting. When they exhaust their hydrogen supply, they will undergo a dramatic transformation, leaving behind remnants that can become neutron stars or black holes. In stark contrast, the red dwarfs, with their lower mass, embark on a much slower journey. They fuse hydrogen at a leisurely pace, extending their lifespans into the trillions of years. This longevity not only allows them to witness the unfolding history of the universe, but it also means they remain stable beacons in the night sky for eons. Imagine these stars as ancient storytellers, quietly observing the cosmos as it evolves around them. The yellow dwarfs, like our own sun, occupy a middle ground. They embody a balance, fusing hydrogen efficiently enough to sustain their luminosity for several billion years. This stability is crucial for life on Earth, as our planet orbits in a harmonious zone where conditions are just right for life to thrive. The sun's presence is more than just a source of light. It serves as a nurturing force that has influenced the development of ecosystems, weather patterns, and even the very rhythms of life itself. Reflect on the remarkable diversity of these stars. Each one tells a story that contributes to the grand narrative of the universe. The light from a distant red dwarf, flickering gently across the void, has traveled for countless years, offering a glimpse into a time long past. Meanwhile, the cerulean brilliance of a blue giant captivates the imagination with its ferocity, marking the fleeting beauty of a stellar life destined for a spectacular end. The significance of main sequence stars extends beyond their individual lifespans. They are the engines of nucleosynthesis, the process by which elements are forged within their cores. As these stars burn through their hydrogen, they produce helium and eventually, in the more massive stars, heavier elements such as carbon, oxygen, and iron. These elements are essential building blocks for planets and life itself. The cosmic dance of fusion and creation echoes the cycles we observe in nature, where life emerges from the remnants of stars, continuing a legacy that spans eons. One cannot help but wonder about the interconnectedness of these celestial bodies. How do they influence one another in the vast expanse of space? The answer lies in the gravitational interactions and the life cycles of stars. When massive stars explode in supernovae, they scatter their enriched materials across the galaxies, seeding new star systems with the necessary ingredients for life. This cosmic recycling ensures that the legacy of one generation of stars becomes the foundation for the next, highlighting the beauty of continuity in the universe. As we consider the stories of these main sequence stars, we may find ourselves reflecting on our own existence. Just as stars evolve and transform, so too do we navigate our paths through the universe. The stability offered by main sequence stars serves as a reminder of the delicate balances in our lives and the importance of nurturing the connections that sustain us. In a way, the main sequence phase can be seen as a metaphor for our own journeys. It is a period of growth, stability, and unfolding potential. Each star shines brightly, contributing its light to the cosmic tapestry, just as we contribute our unique presence to the world around us. As we gaze up at the night sky, let us take a moment to appreciate the intricate web of connections that exists between us and these distant giants, each of us a thread in the grand design of the universe. The saga of main sequence stars is a testament to the power of stability amid the chaos of the cosmos. They are the steady hearts of galaxies, illuminating the dark and providing a sanctuary for the birth of worlds. In their brilliance, we find inspiration and a deeper understanding of our place in this vast expanse. The story of these stars is not merely a scientific account. It is a profound exploration of existence itself, inviting us to wonder about the mysteries that lie beyond our reach. Chapter 4. Red Giants, the transformation begins. The journey of a star transforms profoundly as it ages, and this evolution leads us to the magnificent phase of red giants. These celestial behemoths emerge from the stable existence of main sequence stars, like a vibrant sunset signaling the end of day yet heralding a new dawn. Imagine the serenity of a day fading into twilight, where warmth lingers in the air and the sky shifts into brilliant hues. This is a fitting metaphor for the transformation from a main sequence star to a red giant. As a main sequence star exhausts its hydrogen fuel in the core, a remarkable transition begins. The core, once a bustling center of hydrogen fusion, starts to contract under the weight of gravity, a relentless force that compels the star's innermost layers to compress. Picture this contraction as a gentle squeeze, an embrace of cosmic forces that draws energy inward. The temperature rises dramatically in the shrinking core, reaching levels that ignite a new chapter in the star's life. Around this contracted core, hydrogen continues to burn, but now it does so in a shell surrounding the core, leading to a fascinating phenomenon known as hydrogen shell burning. This layer of hydrogen fuses into helium, releasing a tremendous amount of energy that pushes outward. This expansion creates a pressure that fights against gravitational collapse, but it also causes the outer layers of the star to swell. Envision a balloon being inflated, expanding outward with a soft, gentle pressure. The outer layers of the star grow larger and cooler, transforming the star into a red giant, its surface temperature dropping, and its color shifting to a warm, fiery red. The luminosity of these red giants is astounding. They can shine with a brilliance that dwarfs their main sequence selves, illuminating the cosmos in a show of vibrancy. Imagine the glow of a bonfire on a chilly night, casting flickering shadows and warmth all around. Red giants can be thousands of times more luminous than our sun, a beacon of energy released from the hydrogen shell fusion, radiant and inviting. As the core continues to contract and the outer layers expand, the star enters a critical phase of its life cycle, one that leads to helium fusion. Once the core temperature reaches the threshold necessary for helium fusion, the transformation deepens. Helium, born from the remnants of hydrogen, becomes the new fuel, igniting a process that creates heavier elements. Imagine the quiet hum of a furnace as it begins to burn a new kind of fuel, creating a different kind of warmth and light. Helium fusion, which occurs in a process known as the triple alpha process, fuses 3 helium nuclei into carbon. This is not just a simple reaction, it is a moment of cosmic alchemy, where the elements we cherish on Earth begin to form in the hearts of dying stars. The energy released in this process creates even more outward pressure, allowing the star to maintain its size and luminosity for a time. Consider the words of a great astrophysicist who once said, "The universe is under no obligation to make sense to you." This profound statement captures the wonder of the cosmic processes at play. The transformation into a red giant is a beautiful yet chaotic dance of forces, where the balance between gravity and pressure shifts continually. It is a reminder that our understanding of the universe is but a glimpse into its grand complexity. As red giants continue to evolve, they reach a pivotal point where the balance of forces becomes precarious. The core, now rich in carbon, begins to feel the weight of its own existence, a heavy burden that can lead to further transformations. Imagine a towering mountain, majestic yet under strain, its peak reaching for the sky, while its base struggles to hold it aloft. The life of a red giant is not just a tale of expansion and luminosity, it is also a narrative of creation. During this phase, elements formed in the cores of these giants are scattered throughout the cosmos when they eventually shed their outer layers, enriching the interstellar medium with the building blocks for future stars and planets. Visualize this act of giving as a cosmic seed scattering, nurturing the next generation of celestial bodies in the vast expanse of space. As we contemplate the life cycle of stars, we are reminded that each transformation, each stage, is a necessary part of the story. The evolution from main sequence to red giant signifies not just the aging of a star, but a critical moment in the cosmic dance of creation and destruction. It is a time of brilliance, where old stars make way for new ones, and the cycle of life continues in the universe. In the grand tapestry of the cosmos, the red giant phase serves as a poignant reminder of the inevitable changes that all stars undergo. As we witness these transformations, we are invited to reflect upon our own existence and the cycles of change in our lives. The universe, in all its complexity, offers us lessons in resilience and renewal, urging us to embrace the beauty of transformation. As the core of a red giant contracts, the pressures mount, leading to a transformative interplay of forces that shapes its destiny. The hydrogen shell burning continues, providing a steady source of energy that sustains the star's expansive form. Yet beneath this vibrant exterior, the core is evolving too. The process of helium fusion gradually takes center stage, marking a significant transition in the life of the star. Imagine a pot simmering on the stove, where the heat beneath causes the ingredients to change. In the red giant's core, the temperature rises to a critical threshold, initiating the fusion of helium into carbon through the triple alpha process. This moment is not merely a shift in the star's internal dynamics. It is a moment of creation, where new elements are forged in the heart of the star. The energy released from this fusion reaction counterbalances the gravitational pull, allowing the red giant to maintain its immense size and brightness. This phase of helium fusion brings forth another layer of complexity. The core, now rich in carbon, undergoes further changes as the star ages. The outer layers continue to expand and cool, further enhancing the red giant's characteristic red hue. This transition is not just a visual spectacle. It signifies a star's journey toward the end of its life cycle. The outer envelope of the star may swell dramatically, leading to extraordinary sizes that can engulf the orbits of nearby planets. Imagine gazing upon a colossal sphere of glowing gas, its surface shimmering with the light of countless nuclear reactions. This is the manifestation of stellar evolution, a visual representation of the life-giving energy that sustains life on distant worlds. The luminosity of red giants is a marvel unto itself. These stars can shine with a radiance that is thousands of times greater than that of our sun. Picture a lantern illuminating a dark path, casting light far and wide, creating an atmosphere of warmth and comfort. The energy produced through hydrogen shell burning and helium fusion creates a spectacle that can be seen across vast distances. In this phase, red giants are among the brightest objects in the night sky, guiding the way for astronomers and stargazers alike. As we contemplate the significance of helium fusion, we are reminded of the interconnectedness of all elements in the universe. Each fusion reaction, each moment of stellar creation, contributes to the rich tapestry of the cosmos. Helium, once considered merely a byproduct of hydrogen fusion, becomes a vital player in the creation of heavier elements, leading to the formation of oxygen, neon, and eventually, elements like iron that are essential for the existence of planets and life itself. Can you envision the profound implications of this? As red giants exhaust their helium fuel, They become the crucibles for the elements that will one day form the planets, moons, and even the very atoms that make up our own bodies. Each star that transforms enriches the universe, scattering its elements across the cosmos like seeds carried by the wind. Throughout history, remarkable figures have sought to understand these processes. One such luminary, a pioneer in stellar astrophysics, remarked, "We are made of star stuff." This sentiment encapsulates the essence of our connection to the cosmos, reminding us that the very elements that compose us were once forged in the hearts of stars, now long extinguished. As red giants continue their evolutionary journey, they approach a critical juncture. The balance between gravitational forces and the energy produced by nuclear fusion becomes increasingly delicate. The core, now a blend of carbon and oxygen, may reach a point where it can no longer sustain the outward pressure needed to maintain its grand size. This precarious state sets the stage for a series of dramatic events that will ultimately reshape the star and its surroundings. The outer layers of a red giant may begin to shed, creating stunning nebulae that are often observed in the night sky. Imagine the sight of a vibrant cloud of gas and dust, illuminated by the fading light of a star as it disperses into the cosmos. This process is not only a spectacular finale for the red giant, but also a crucial moment in the life cycle of the universe. The materials released during this shedding enrich the interstellar medium, providing the building blocks for new stars and planetary systems. Reflecting on these transformations, one might wonder about the nature of change itself. Why do stars go through such profound evolutions? The answer lies in the fundamental laws of physics that govern their existence. Stars, like all entities in the universe, are subject to the relentless march of time. As they evolve, they reveal the intricate dance of matter and energy, a process that underscores the beauty and complexity of the cosmos. As we embrace the narrative of red giants, we are invited to consider our place within this vast universe. Each transformation, each moment of creation, resonates with the cycles of our own lives. The journey from main sequence star to red giant serves as a reminder that change is not only inevitable, but also a source of wonder and renewal. The radiant glow of red giants beckons us to reflect on our own journey, urging us to celebrate the beauty of transformation in all its forms. In the heart of the cosmos, stars like red giants illuminate the night, casting light on the mysteries of existence. Their story is a testament to the resilience of creation, reminding us that even as stars approach their end, they give rise to new beginnings. Each flicker of light is a whisper of the past, a promise of the future, and an invitation to marvel at the intricate dance of the universe. Chapter 5: Supernovae, the explosive death of stars. As red giants swell in their majestic transformation, they reach a pivotal moment in their existence, the point where their journey culminates in an extraordinary explosion known as a supernova. This cataclysmic event is not just the end of a star. It heralds the birth of new elements and the reshaping of the surrounding cosmos. To understand a supernova, we must first consider the delicate conditions that lead to this explosive finale. At the heart of a red giant, the core, which has contracted under gravity's relentless grip, becomes incredibly hot and dense. As temperatures soar, reaching millions of degrees, helium fusion ignites within the core. Imagine an intense heat radiating from this compact center, where helium atoms merge to form heavier elements like carbon and oxygen. However, the star's life is fleeting. As it continues to burn these elements, it eventually exhausts its fuel. The balance between gravitational collapse and the outward pressure from nuclear fusion begins to falter. What happens when a star can no longer sustain this balance? It succumbs to gravity, with catastrophic consequences. When the core's fuel runs out, the outer layers of the star fall inward, compressing further, while the core's temperature spikes even higher. This process is akin to a tightly coiled spring, wound up and ready to release its energy in a dramatic fashion. As gravity pulls the outer layers toward the core, They rebound off the incredibly dense core, resulting in a shockwave that travels outward. This shockwave disrupts the outer shell of the star, causing it to explode with an unparalleled ferocity. The sheer energy released in a supernova can outshine entire galaxies for a brief moment in time. The mechanics of the explosion are as fascinating as they are complex. In the final moments of a supernova, the outer layers of the star are expelled into space at staggering velocities. Envision a cosmic fireworks display with materials flung outward in all directions, creating a brilliant spectacle against the dark backdrop of space. The explosion disperses elements forged in the stellar furnace, such as iron, nickel, and even heavier elements that are vital for the formation of planets, stars, and potentially life itself. In the words of the astrophysicist Neil deGrasse Tyson, "We are stardust brought to life, then empowered by the universe to figure itself out." But what is the impact of these explosions on their surroundings? The remnants of a supernova create nebulae, vast clouds of gas and dust rich in new elements. These nebulae serve as the nursery for new stars and solar systems, perpetuating the cycle of cosmic creation. Imagine drifting through these colorful clouds, where the remnants of dead stars blend with fresh cosmic dust, creating an environment ripe for new stellar births. The elements cast out into the universe provide the building blocks for the next generation of stars and planets, repeating the cycle that began with the first supernovae billions of years ago. Throughout history, specific supernovae have captured the attention and imagination of astronomers and stargazers alike. One of the most famous is SN 1054, which was observed by Chinese astronomers nearly a millennium ago. This supernova exploded in our Milky Way galaxy, leaving behind the Crab Nebula, a stunning remnant that continues to be studied today. The light from this explosion reached Earth, illuminating the night sky and creating a lasting legacy that has inspired countless generations. The Crab Nebula itself is a dynamic environment, pulsating with energy and serving as a laboratory for understanding the aftermath of stellar death. Another noteworthy supernova is SN 1987A, which occurred in the Large Magellanic Cloud. This event marked a pivotal moment in modern astronomy, as it was the closest supernova observed in 4 centuries. The visible light from SN 1987A arrived on Earth in a brilliant burst, providing astronomers with a unique opportunity to study the dynamics of a supernova in real time. Astrophysicists like Robert Kirshner, who observed the event, noted its significance, stating, "The supernova is like a laboratory that gives us a chance to test our theories about the universe." What can we learn from these explosive events? Supernovae not only enrich the universe with new elements, but also influence the formation of new stars. Their shock waves compress nearby gas and dust, triggering the birth of protostars in their vicinity. It is a cosmic dance of creation and destruction, where the remnants of stellar deaths give rise to new celestial bodies. Consider the vastness of space, where supernova remnants create intricate structures that can last for millions of years. These remnants are not merely the remains of stars, they are the seeds of new beginnings. The cycle of stellar evolution continues, with each supernova carving the path for the next generation of stars and planets. As we reflect on the significance of supernovae, let us remember that they are not just fiery explosions in the cosmos. They are pivotal moments in the grand narrative of the universe, linking the past to the future. Each explosion is a testament to the life cycle of stars, reminding us that even in death, there is the promise of new life. What does this cycle tell us about our place in the universe? It underscores the interconnectedness of all things, revealing that we too are part of this grand cosmic story. The journey from cosmic dust to protostar, to main sequence star, to red giant, and finally to supernova is a remarkable odyssey. Each phase contributes to the ever-evolving universe, creating a rich tapestry of existence. As we gaze up at the night sky, let us marvel at the stars and remember the powerful forces that shape them. Supernovae serve as a reminder of the beauty and complexity of life beyond our planet, inviting us to ponder the mysteries that lie within the cosmos. The aftermath of a supernova is not merely a conclusion, but a new beginning, echoing the cyclical nature of the universe. The remnants from these celestial explosions often give rise to spectacular phenomena known as supernova remnants, which are both visually mesmerizing and scientifically significant. These remnants are typically composed of gas and dust, expanding outward at incredible speeds. Picture a cosmic cloud illuminated by the remnants of a star's fiery end, where the very elements that once formed the star are now liberated into the cosmos. Among the notable remnants, the Crab Nebula stands as a testament to the power of a supernova. Born from the explosion of SN 1054, it is a living laboratory where cosmic processes unfold. The pulsar at its center, a rapidly rotating neutron star, emits beams of radiation that sweep across the sky like a cosmic lighthouse. This pulsar, the core of the once mighty star, rotates with remarkable precision, offering insights into the physics of extreme conditions, where gravity, magnetic fields, and speed converge in a dance of energy. What might we discover within these remnants? As we study the Crab Nebula and others like it, we learn how the elements dispersed by supernovae contribute to the cosmic environment. The iron and other heavy metals produced in these stellar explosions enrich the interstellar medium, fostering the birth of new stars and planetary systems. Imagine the dust settling across the cosmos, ready to coalesce once again, nurturing the next generation of celestial bodies. Each supernova, then, is a crucial player in the grand narrative of cosmic evolution. Consider the implications of these events on the formation of our own solar system. The elements found in the Earth, carbon, oxygen, and iron, are thought to have originated in supernovae long before our planet took shape. This connection reveals a profound truth. We are tied to the universe in ways that transcend time and space, composed of the very elements forged in the hearts of stars. The story of our existence is inextricably linked to the explosive deaths of these celestial giants. As we explore the significance of supernovae in history, we cannot overlook the impact of SN 1987A. This supernova not only provided a unique opportunity for scientists to observe an explosive stellar death, but also inspired a surge of interest in astrophysics. Its proximity allowed astronomers to unravel the mechanics of supernova explosions and their remnants in real time. What insights did they gather? Observations revealed that the light and radiation from SN 1987A were not just fleeting wonders, but offered critical data about the life cycles of massive stars. The event challenged existing models and deepened our understanding of stellar evolution. The study of supernovae has deepened our grasp of the universe's expansion, leading to the discovery of dark energy, a mysterious force driving galaxies apart. This unexpected revelation stemmed from observing distant supernovae, which appeared dimmer than anticipated. What does this tell us about the cosmos? It suggests that the universe is not static, but dynamic, evolving with time in ways that continually surprise and challenge our understanding. Throughout history, supernovae have not only shaped the cosmos, but have also left an indelible mark on human culture. Ancient civilizations often recorded these events. The appearance of a bright new star in the sky was met with awe and reverence. These celestial explosions inspired myths and folklore, transforming the night sky into a canvas painted with the stories of gods and heroes. Imagine the stargazers of old, their eyes fixed on the heavens as a new light broke through the darkness. In some cultures, such events were seen as omens, signaling change or transformation. These interpretations reflected a deep human connection to the cosmos, reminding us that even in a scientific age, the universe continues to spark wonder and curiosity. As we embrace the knowledge gained from studying supernovae, we must also acknowledge the limitations of our understanding. The universe, vast and enigmatic, still holds many secrets. Each supernova observed brings forth new questions, inviting future generations of astronomers and scientists to explore further. What mysteries lie in the shadows of the cosmos, waiting to be illuminated by the light of dying stars? In this intricate dance of creation and destruction, supernovae serve as powerful reminders of the impermanence of life in the universe. They embody the transient nature of existence, where even the most magnificent stars meet their end. Yet from this end comes the promise of new beginnings. Just as a forest thrives after a fire, the cosmos rejuvenates itself through these explosive events, crafting a rich and diverse landscape of stars and planets. As we continue to gaze upward, let us remember that the night sky is alive with stories of birth, death, and rebirth. Each flicker of light represents countless tales of transformation, echoing through the corridors of time. The supernovae that punctuate the fabric of the universe remind us that we are part of a grand narrative, woven together by the stellar explosions that shaped our world. What will we uncover as we continue to explore this cosmic journey? The possibilities are as boundless as the universe itself, inviting us to ponder our place within it. Chapter 6. Neutron Stars, the Remnants of Supernovae. In the aftermath of a supernova, the universe is forever altered, as the remnants of a once mighty star give birth to a new celestial entity, the neutron star. Imagine the brilliance of the supernova explosion fading, leaving behind a compact, dense core. It is within this core that something extraordinary happens. When a star with a mass greater than a certain threshold exhausts its nuclear fuel, the core collapses under the relentless pull of gravity. The outer layers are violently expelled, scattering elements throughout the cosmos, while the core itself becomes a neutron star, a remnant so dense that its very structure challenges our understanding of matter. Neutron stars are birthed from this cataclysm, characterized by an astonishing density. Picture a mass greater than that of our Sun, compressed into a volume no larger than a city. A single teaspoon of neutron star material would weigh as much as an entire mountain. This extreme density arises because, during the collapse, electrons and protons combine to form neutrons, particles that are typically found within atomic nuclei. The result is a star primarily composed of neutrons, held together by the force of gravity and a mysterious interaction known as neutron degeneracy pressure. This unique structure creates conditions unlike any other in the universe, where the laws of physics bend and twist. As we contemplate the characteristics of neutron stars, we find ourselves drawn to their surface, which is the most extreme environment imaginable. The temperature can soar to millions of degrees, and the gravity at the surface is immense, approximately 2 billion times stronger than that of Earth. Can you envision standing on such a surface? The gravitational force would crush anything within reach, pulling it into a swirling abyss. The magnetic fields surrounding these stars are also staggering, often 1 trillion times stronger than Earth's magnetic field. They twist and turn like ribbons of light, creating an environment rich in energy and mystery. Among the most fascinating aspects of neutron stars are pulsars, a specific type of rotating neutron star. As these stars spin, they emit beams of electromagnetic radiation from their magnetic poles. Imagine a lighthouse, its beams sweeping across the dark ocean, guiding ships safely to shore. Similarly, pulsars send out pulses of radiation that can be detected across vast distances in space. The rotation of a pulsar can be incredibly rapid, with some spinning hundreds of times per second. This pulsating effect, rhythmic and precise, creates a cosmic clock that is extraordinarily reliable. The discovery of pulsars was serendipitous, first unveiled by Jocelyn Bell Burnell in the late 1960s. While observing radio waves from space, she and her colleagues detected a series of regular pulses. At first, they whimsically dubbed these signals "little green men," imagining the possibility of extraterrestrial communication. However, further analysis revealed that these were, in fact, the rhythmic emissions of pulsars, illuminating the night sky with their celestial heartbeat. Bell Burnell's contribution to astrophysics reshaped our understanding of neutron stars, showcasing the beauty of unexpected discoveries in the universe. The significance of neutron stars extends far beyond their mesmerizing properties and the captivating tales of pulsars. In the realm of astrophysics, these stars serve as natural laboratories for exploring the fundamental laws of nature. Their extreme conditions allow scientists to test theories of gravity, nuclear physics, and the behavior of matter under immense pressure. For example, the study of neutron stars can provide insights into the strong nuclear force, the fundamental interaction responsible for binding protons and neutrons within atomic nuclei. This is a force that is not fully understood even in our earthly experiments. Have you ever pondered the impact of neutron stars on the cosmic landscape? Their formation enriches the surrounding space with heavy elements, including gold and platinum, forged in the intense environments of supernova explosions and neutron star mergers. When two neutron stars collide, they create gravitational waves, ripples in spacetime, that can be detected from billions of light years away. The merger of these stellar remnants can also produce kilonovae, dazzling displays of light that outshine entire galaxies for brief moments. These events remind us of the interconnectedness of the universe, where the death of one star can lead to the birth of new worlds and new elements. Neutron stars, with their enigmatic nature, invite us to delve deeper into their mysteries. They challenge our understanding of what is possible in the universe, pushing the boundaries of science and imagination. As we gaze up at the night sky, let us remember that every twinkling star tells a story, and among those stories are the remnants of supernovae, the spectacular neutron stars, and the pulsars that pulse like the very heartbeat of the cosmos. What wonders lie ahead as we continue to explore these celestial enigmas? As we explore the fascinating world of neutron stars, we are struck by their remarkable characteristics. The density of a neutron star is so extraordinary that it challenges our comprehension of matter itself. Within this compact celestial body, the structure is layered, with an outer crust composed of atomic nuclei and electrons, a region of superfluid neutrons, and a core that may contain quark matter. Imagine a place where the very fabric of reality is stretched thin, where neutrons exist in a state of superfluidity, flowing without viscosity. This state allows them to move freely, providing insights into quantum mechanics that remain elusive on Earth. But what does it mean for a star to exist in such extreme conditions? The immense gravitational pressure compresses neutrons to the point where they begin to behave differently than in any other state of matter. It is a realm where the fundamental forces of nature collide, creating an environment ripe for discovery. Scientists are eagerly studying these conditions, hoping to unlock the secrets of the universe, perhaps even addressing questions about dark matter and the very essence of space and time. One of the most intriguing aspects of neutron stars is the phenomenon of pulsars, which serve as cosmic lighthouses. Envision a pulsar spinning rapidly, its beams of radiation sweeping across the cosmos like a lighthouse beam cutting through fog. These stars emit radiation across various wavelengths, including radio and X-rays, producing pulses that can be detected by telescopes on Earth. The precision of these pulses is astonishing. Some pulsars exhibit such regularity that they can be used as cosmic clocks, with a consistency rivaling the most accurate timekeeping devices we have on our planet. The incredible regularity of pulsar emissions leads to intriguing questions. How can such distant objects maintain such a precise rhythm? This consistency can be attributed to their rapid rotation and strong magnetic fields. As a pulsar spins, its magnetic field generates a powerful electric field, accelerating charged particles to nearly the speed of light. This process creates beams of radiation that pulse in and out, as the star rotates, akin to a cosmic metronome marking the passage of time. The study of pulsars has not only expanded our understanding of neutron stars, but has also illuminated the path of gravitational wave research. When two neutron stars orbit each other, they emit gravitational waves, ripples that travel through the fabric of space-time. Imagine these waves as the echoes of a cosmic symphony, resonating through the universe. The detection of these waves has opened a new chapter in astrophysics, allowing scientists to observe celestial events that were previously invisible to our senses. Consider the significance of neutron stars as laboratories for testing the limits of our understanding. The extreme gravitational fields of neutron stars challenge our theories of physics, particularly in the realm of general relativity. When we observe the behavior of matter under such conditions, we gain insight into how gravity influences the universe on a grand scale. Could the mysteries of black holes, their formation, and their behavior be illuminated through the study of neutron stars? This tantalizing connection invites us to ponder the intricate web of cosmic events that shape our universe. In a broader sense, neutron stars form a crucial part of the cosmic ecosystem, contributing to the life cycle of galaxies. When these stars reach the end of their existence, often colliding with other neutron stars or black holes, they create some of the most energetic events known to humankind. The mergers of neutron stars can produce kilonovae, brilliant flashes that outshine entire galaxies for a fleeting moment. In these explosive events, heavy elements are forged in the crucible of extreme conditions, scattering precious materials throughout space. As we reflect on the significance of neutron stars, we find ourselves acknowledging their role in the grand tapestry of the universe. They serve as both creators and destroyers, enriching the cosmic landscape with the elements that form planets and, ultimately, life. Each neutron star is a testament to the intricate interplay of forces that govern the cosmos, a reminder that even in death, stars contribute to the birth of new celestial bodies. What does it mean for us, as inhabitants of this universe, to contemplate the lives of stars that have come before us? It invites us to embrace the interconnectedness of all things, to recognize that our existence is intricately woven into the cosmic narrative. The remnants of supernovae, the formation of neutron stars, and the pulsars that pulse through the darkness serve as a reminder of the cycles of creation and destruction that define our universe. As we continue our journey through the cosmos, let us pause to marvel at these celestial wonders. The neutron stars, with their extraordinary properties and profound significance, beckon us to explore further, to seek knowledge, and to uncover the mysteries that lie beyond our reach. What other secrets do they hold, waiting patiently to be discovered by those who dare to look up at the night sky and wonder? In the heart of a neutron star, the conditions are so extreme that they challenge our understanding of the very fabric of matter. Picture a realm where the laws of physics seem to stretch and bend, a place where the behavior of particles defies our everyday experiences. Within this dense core, neutrons are packed so tightly that they may form a lattice structure, with some theories suggesting that quarks, the building blocks of protons and neutrons, could be liberated from their confines. This leads us to ask, what might these strange forms of matter reveal about the universe at its most fundamental level? The unique structure of neutron stars provides a rare opportunity for scientists to explore phenomena that are otherwise beyond reach. The intense gravitational field surrounding them can warp space-time itself, creating an environment ripe for testing Einstein's theories of relativity. Imagine observing light bending and warping as it travels past such a massive body, a cosmic dance of gravity and light that illustrates how interconnected everything in the universe truly is. As we deepen our understanding of neutron stars, we cannot overlook their role in the grand narrative of cosmic evolution. The elements forged in the explosive death of massive stars enrich the interstellar medium, providing the raw materials for the next generation of stars and planets. This cycle of birth and rebirth, reminiscent of the cycle of life itself, is a testament to the enduring legacy of stellar remnants. Have you ever considered how the gold in your jewelry or the iron in your blood may trace its origins back to such cataclysmic events. The very atoms that comprise our bodies are formed in the hearts of stars, only to be scattered across the universe in explosive finales. Pulsars, the rotating neutron stars that emit beams of radiation, serve as cosmic beacons, offering insights into the nature of time and space. Some pulsars are known as millisecond pulsars, spinning with such incredible speed that they can complete a rotation in mere milliseconds. Imagine standing on the surface of one of these pulsars, feeling the rapid heartbeat of the universe resonating beneath your feet. The precision of their rotation allows them to act as natural clocks, providing a reliable mechanism to test our understanding of gravity and the fundamental forces at play in the cosmos. The significance of neutron stars extends beyond their fascinating characteristics. They also serve as a bridge to understanding the universe's most enigmatic phenomena. The study of neutron stars and their pulsars has implications for gravitational wave astronomy, a field that has blossomed since the first detection of gravitational waves. When neutron stars collide, they create ripples in space-time that can be observed on Earth, enabling scientists to probe the depths of the universe and uncover secrets hidden within its depths. In contemplating the vastness of the cosmos and the role of neutron stars within it, we are reminded of the interconnectedness of all things. Each neutron star is a monument to the life cycle of stars, a reminder that even in their demise, they contribute to the ongoing evolution of the universe. They invite us to ponder the fundamental questions of existence. What lies beyond our current understanding? How do the forces of nature shape the fabric of reality? As we journey forward, let us take a moment to appreciate the intricate web of cosmic events that give rise to the universe we inhabit. The pulsars that flash in the night sky, the neutron stars that beckon from the depths of space, and the remnants of supernovae that enrich the cosmic dust are all woven into a narrative that is as beautiful as it is complex. What other secrets might these stellar phenomena hold, waiting patiently for us to uncover? Chapter 7. Black Holes, the ultimate fate of massive stars. The life cycle of massive stars leads them to their most dramatic conclusion, one that captivates both the imagination and the intellect, the formation of black holes. To understand how a massive star transforms into one of these enigmatic objects, we must first consider the conditions that set the stage for such a profound transformation. When a star exhausts its nuclear fuel, a cascade of events unfolds. Massive stars, those that exceed a certain mass threshold, experience an accelerated evolution compared to their less massive counterparts. Picture a star that has spent millions of years fusing hydrogen into helium, transitioning through various stages, including the red giant phase. As it reaches the end of its life, the core collapses under the immense gravitational pull, while the outer layers are expelled in a brilliant supernova explosion. This spectacular finale is not merely an end, but a precursor to the birth of something even more mysterious. As the core collapses, it shrinks to a point where the gravitational forces become so strong that not even light can escape its grasp. This boundary, known as the event horizon, marks the threshold of a black hole. Imagine standing at the edge of an immense waterfall, where the waters cascade down into a dark abyss below. The event horizon is akin to that precipice, a point of no return. Crossing it means entering a realm where the laws of physics as we know them begin to break down. Beyond this horizon exists the singularity, a point where matter is compressed to such an extent that density becomes infinite, and our understanding of space and time dissolves. The idea of a singularity challenges our perceptions of reality. What is it like at this point? It's a question that has piqued the curiosity of many brilliant minds. Theoretical physicist Stephen Hawking once remarked, "The only black hole I have ever been in is the one I have been trying to understand." This pursuit of understanding reflects the deep human desire to comprehend the unfathomable. Black holes are not a singular phenomenon. They come in various types, each with their own remarkable characteristics. The most commonly known are stellar black holes, which form from the remnants of massive stars after they have exploded in supernovae. These black holes typically possess masses several times that of our Sun, compacted into an incredibly small volume. Then there are supermassive black holes, found at the centers of galaxies, including our own Milky Way. How do these colossal entities come into existence? The leading theory suggests that they may form from the merger of smaller black holes, or perhaps through the slow accumulation of mass over billions of years, drawing in gas, dust, and stars. Imagine a cosmic vortex, quietly accumulating matter and growing larger, its gravitational influence shaping the very structure of the galaxy around it. Intermediate black holes represent a less understood category. These black holes sit between stellar and supermassive black holes in terms of mass. Their formation is still a subject of research and debate among astrophysicists. Some propose they could arise from the merger of several stellar black holes, while others suggest they may form directly from the collapse of massive clusters of stars. This ambiguity adds to the allure of black holes, as they provoke questions about the fundamental processes governing our universe. The role of black holes in galaxy formation is pivotal. They serve not only as endpoints in the life cycle of massive stars, but also as crucial players in the evolution of galaxies themselves. Imagine the gravitational pull of a supermassive black hole at a galaxy's center, influencing the orbits of surrounding stars and gas. This gravitational force can regulate star formation, as matter is drawn toward the black hole, creating a swirling disk of energy known as an accretion disk. In this disk, matter heats up and emits tremendous amounts of energy, often visible as bright jets of radiation shooting out into space. The interplay between black holes and galaxies fosters an intricate relationship that shapes the cosmos. As galaxies collide and merge, their central black holes can also interact, eventually spiraling toward one another and merging to form an even larger black hole. This cosmic ballet underscores how black holes are not isolated phenomena, but rather interconnected components of the universe's grand design. As we ponder the mysteries of black holes, we can't help but marvel at how much we still have to learn. The universe whispers its secrets, inviting us to explore deeper into the fabric of reality. What is it about these dark, enigmatic objects that draws our curiosity? Perhaps it is their ability to challenge our understanding of time, space, and the very nature of existence. In the vast expanse of the cosmos, black holes stand as testaments to the life cycle of stars and the ever-evolving landscape of galaxies. They remind us that even in the depths of darkness, there is a dance of creation and destruction, a reminder that the universe is a place of wonder and endless discovery. What lies beyond the event horizon? What new realms of knowledge await those brave enough to seek answers? These questions linger in the minds of scientists and dreamers alike, urging us forward in our quest to uncover the mysteries of existence. The intricate cycle of stellar evolution does not merely end with the formation of black holes. It encompasses a broader narrative that highlights their significance in the cosmos. As we ponder the profound implications of these enigmatic objects, we must also consider how they vary in size and influence. Stellar black holes, the most common type, are remnants of massive stars that have undergone supernova explosions. Their formation is a testament to the delicate balance of forces acting within a star. When a massive star collapses, the energy released is not just a destructive force, but a transformative one. It scatters elements forged in stellar interiors across the universe, enriching the interstellar medium with the building blocks of new stars and planets. Can we imagine the impact of such an event? The death of one star can give life to many others, a beautiful cycle of creation and destruction that paints the universe with complexity. Supermassive black holes, on the other hand, present a fascinating challenge to our understanding of cosmic structure. These giants, often found at the centers of galaxies, can possess masses equivalent to millions or even billions of suns. their formation processes remain a topic of intense study. Some theories suggest they might originate from the merger of smaller black holes in the chaotic aftermath of star formation. Others propose that they grow gradually by accumulating gas and dust over eons, drawing in matter like a cosmic vacuum cleaner. Imagine a swirling whirlpool at the center of a galaxy, its gravitational pull influencing the orbits of stars and gas clouds alike. This dynamic interplay speaks to the role supermassive black holes play in the evolution of galaxies. Intermediate black holes add another layer of intrigue to this cosmic hierarchy. While their existence has been theorized for decades, evidence for their presence remains elusive. These black holes, with masses between stellar and supermassive black holes, could provide critical insights into the processes that govern black hole formation and growth. Where do they fit in the cosmic puzzle? Are they remnants of a previously unknown evolutionary pathway, or do they serve as stepping stones in the journey of black hole evolution? Each discovery related to these mysterious entities deepens our understanding of the universe's structure. The relationship between black holes and galaxy formation is a captivating story in itself. The gravitational influence of a supermassive black hole can affect star formation rates within its host galaxy. When gas and dust accumulate around these colossal entities, they form accretion disks, rotating disks of material that spiral into the black hole. As matter accelerates and heats up, it emits energy in the form of radiation, often visible across vast distances. Imagine this disk as a brilliant ring of light, illuminating the dark void around it, a beacon of energy that signals the presence of a black hole lurking in the shadows. What happens when galaxies collide? The intricate gravitational dance can lead to the merger of their central black holes, creating even more massive entities. This cosmic event can trigger a burst of star formation, a phenomenon known as starburst activity, as gas is compressed and ignited in the wake of the merger. The universe unfolds in a vibrant tapestry of activity, where black holes play a central role in shaping the landscape of galaxies. Consider the consequences of such colossal interactions. The merger of two supermassive black holes can produce gravitational waves, ripples in spacetime, that travel through the universe like echoes of a distant storm. The detection of these waves has opened a new window into the cosmos, allowing us to observe events that were previously beyond our reach. The field of gravitational wave astronomy is still in its infancy, yet it promises to transform our understanding of black holes and the processes that govern their existence. As we explore these realms, we must also confront the philosophical implications of black holes. What do they reveal about our understanding of the universe? The nature of black holes challenges our perceptions of reality, pushing the boundaries of science and philosophy alike. The notion that information may be lost beyond the event horizon has sparked debates among scientists and theorists. Is information truly lost, or can it be recovered in some form? This question resonates deeply, inviting us to ponder the very fabric of existence. In contemplating black holes, we are invited into a realm where the known meets the unknown. They serve as reminders of the limits of our understanding and the vastness of what remains to be discovered. Each new insight into their nature offers a glimpse into the universe's more profound mysteries. As we look to the stars, we are urged to remain curious, to seek answers, and to embrace the beauty of the unknown. The cosmos is a grand narrative, continuously unfolding as stars are born, evolve, and ultimately perish. Black holes, in all their varieties and complexities, are crucial chapters in this story. They remind us that within the darkest corners of the universe there exists a symphony of processes that shape the very nature of reality, urging us to explore, to wonder, and to dream. The formation and existence of black holes is a narrative rich with interconnected themes, seamlessly woven into the cosmic fabric that surrounds us. To fully appreciate their role, one must reflect on the intricate dance of matter and energy that leads to their creation. As massive stars exhaust their hydrogen fuel and collapse, they become catalysts for change, scattering elements throughout the universe. This process serves as the foundation for not only their own demise, but also the birth of new celestial bodies. In the aftermath of a supernova, the remnants of these stars contribute to the cosmic environment. The elements expelled during the explosion, elements forged in the fiery hearts of those stars, become the building blocks of new stars and planets. Picture the universe as a vast garden, where the seeds of new life are sown in the fertile soil left behind by deceased stars. This cycle of death and rebirth underscores the interconnectedness of all celestial phenomena. Black holes, as we have explored, come in various forms, each with a unique story to tell. Stellar black holes, formed from the remnants of massive stars, are often solitary figures in the cosmos. However, their supermassive counterparts, residing at the centers of galaxies, are the true giants of the universe. How do they influence the structures around them? The gravitational pull of a supermassive black hole is not merely a force. It shapes the very architecture of its galaxy. Imagine the intricate pathways of stars and gas, their orbits choreographed by the invisible hand of the black hole's gravity. This gravitational influence extends far beyond mere attraction. It regulates star formation within the galaxy. Gas clouds pulled toward the black hole can compress and ignite, giving rise to new stars, while simultaneously curtailing the birth of others. The balance between creation and destruction is a delicate one, orchestrated by the presence of these enigmatic entities. As we consider the vastness of the universe, we can appreciate how black holes act as both creators and destroyers, reminding us of the cyclical nature of existence. As we ponder the complexity of these forces, we may wonder about the implications of black holes on galactic evolution. Their presence may dictate the paths that galaxies take as they merge and collide. When galaxies collide, the central black holes can spiral toward one another, eventually merging to form an even larger black hole. This cosmic event is not merely a collision. It can trigger dramatic changes in star formation rates, leading to bursts of activity that illuminate the night sky. The merging of black holes is a phenomenon that resonates through space and time, creating gravitational waves that ripple outward, providing a new method for astronomers to explore the universe. The study of black holes also invites philosophical contemplation. They challenge our understanding of reality and the nature of existence itself. What do these dark entities reveal about the universe's fundamental laws? The idea that information may be lost beyond the event horizon raises profound questions about the nature of knowledge and existence. Are we mere observers in a universe governed by forces we cannot fully comprehend? The pursuit of understanding black holes is not just a scientific endeavor. It is a journey through the very fabric of reality. As we navigate these cosmic mysteries, we find that black holes serve as portals to deeper understanding. Each discovery nudges us closer to unraveling the complexities of the universe. The interplay between black holes and the galaxies they inhabit showcases a dynamic relationship that continues to evolve, promising new revelations with each passing moment. In this vast expanse, the journey of black holes is a testament to the interconnectedness of all things. Their existence embodies the cycles of life and death, the creation of stars, and the intricate dance of galaxies. We are reminded that our understanding of the cosmos is but a flicker in the grand tapestry of existence, inviting us to remain curious and open to the wonders that lie ahead. Each question leads to more questions, and with every exploration, we inch closer to comprehending the profound realities that govern our universe. Chapter 8. Stellar Nucleosynthesis, Creating Elements in Stars. In the heart of every star, a remarkable process unfolds, known as nucleosynthesis, the very art of creation that transforms simple elements into the complex building blocks of the universe. As we journey into this celestial realm, it is essential to grasp the essence of fusion reactions, the mechanism through which stars breathe life into new elements. Imagine a vast cauldron of energy, where hydrogen atoms collide with such fervor that they merge, creating helium and releasing a tremendous amount of energy in the form of light and heat. This fundamental reaction, the cornerstone of stellar life, occurs in the cores of stars, where temperatures soar to millions of degrees, creating an environment ripe for transformation. The journey of nucleosynthesis begins with hydrogen, the simplest and most abundant element in the universe. Under the crushing weight of gravitational forces, hydrogen nuclei collide at incredible speeds. As they overcome their natural repulsion, they fuse together, forming helium. This fusion process is not merely a scientific phenomenon. It is a dance of particles that produces the energy sustaining a star for billions of years. Picture a delicate balance maintained in the star's core, an equilibrium between the outward pressure generated by nuclear fusion and the inward pull of gravity. This balance allows stars to shine brightly, illuminating the cosmos and providing the necessary conditions for more complex elements to form. But the story does not end with helium. As stars evolve, they reach a tipping point when hydrogen in their cores diminishes. In the case of medium-sized stars, like our Sun, they swell into red giants, igniting helium fusion in their cores. This new phase of stellar life leads to the creation of even heavier elements, such as carbon and oxygen, through a process called triple alpha fusion. Imagine the heat and pressure within the core, igniting a new wave of creation, as 3 helium nuclei unite to form carbon, with energy radiating outward, illuminating the surrounding layers of the star. In the more massive stars, the journey continues, as they evolve through successive stages of nucleosynthesis, each marked by the creation of heavier elements. After carbon, stars fuse to create oxygen, neon, and beyond, culminating in elements as heavy as iron. This progression is a symphony of reactions, where each new element is born from the ashes of its predecessors. As the great physicist and cosmologist Carl Sagan once said, "The cosmos is all that is, or ever was, or ever will be." This statement encapsulates the essence of nucleosynthesis. Every element we encounter, from the oxygen we breathe to the iron in our blood, is forged in the hearts of stars. As we reflect on the immense scale of these processes, how do we reconcile the birth of elements with our own existence? The answer lies in the stars' ultimate fate. When massive stars exhaust their nuclear fuel, they cannot sustain the delicate balance any longer. The core collapses, leading to a spectacular supernova explosion. This cataclysmic event is not just an end. It is a rebirth, a moment when the elements forged within the star are scattered across the universe. Imagine a cosmic fireworks display, where the remnants of a star explode into a myriad of elements, enriching the surrounding space with the very ingredients of life. Through supernovae, elements heavier than iron are created in the chaos of the explosion itself, a process known as nucleosynthesis in explosive environments. The temperatures and pressures during these events reach unimaginable levels, allowing for rapid neutron capture, a process that produces elements such as gold, silver, and uranium. Picture these elements being hurled into the cosmos, seeds of possibility that will eventually coalesce into new stars, planets, and perhaps even life itself. The implications of stellar nucleosynthesis stretch far beyond the immediate vicinity of a star. The dispersal of elements through supernovae establishes a rich tapestry of chemical diversity within galaxies. As this cosmic dust settles, regions of gas and dust begin to condense, forming new stars and planetary systems, a cycle that repeats over eons. Each generation of stars contributes to the chemical evolution of the universe, creating the conditions necessary for the emergence of complex structures. Consider this. Every time we gaze at the night sky, we are witnessing the legacy of stellar nucleosynthesis. The stars we see are not merely points of light. They are the remnants of ancient giants, each carrying within them the history of cosmic creation. As the astrophysicist Neil deGrasse Tyson eloquently put it, we are stardust brought to life, then empowered by the universe to figure itself out. This profound connection between our existence and the stars, emphasizes the importance of understanding the processes that give rise to the elements that make up our world. Furthermore, the study of nucleosynthesis has significant implications for our understanding of the universe's chemical composition. By analyzing the light emitted from stars and the remnants of supernovae, astronomers can infer the abundance of various elements throughout the cosmos. This knowledge allows us to trace the pathways of element formation and the distribution of matter. Imagine being able to peer back in time, deciphering the story of our universe written in the light of distant stars. The intricate processes of stellar nucleosynthesis remind us of the delicate balance of forces at play in the universe. It is a dance of creation and destruction, where the end of one star becomes the beginning for another. Each supernova not only enriches the cosmos, but also sets the stage for the next generation of stars and planets. This cosmic recycling is a testament to the interconnectedness of all matter, a reminder that the very elements that comprise our bodies and our world were once forged in the fiery hearts of stars. As we contemplate the journey of nucleosynthesis, we begin to understand our place in this grand cosmic narrative. The elements that make up our planet and our bodies are the result of ancient processes that span billions of years. Just as stars are born, live, and die, so too do the elements they create, weaving a complex web of existence. Within this context, we may find solace in the knowledge that we are part of a much larger story, one that connects us to the stars above. What does it mean to be made of stardust? It is a reminder of the beauty and complexity of life itself, a celebration of the cosmic forces that shape our reality. The process of nucleosynthesis transcends mere scientific explanation. It is a profound invitation to reflect on the interconnectedness of all things. In every breath we take and every moment we live, we carry the echoes of the stars within us, reminding us that we are part of a universe alive with possibilities. The aftermath of a supernova is not just a moment of destruction, it is a catalyst for cosmic rebirth. As the remnants of the exploded star scatter across the vastness of space, they create a fertile environment for the formation of new stars, planets, and, eventually, life. Imagine this cosmic dust drifting through the galaxy, each particle a potential building block for future celestial bodies. These remnants, enriched with a diverse array of elements forged within the star, become the raw materials from which new solar systems arise. The role of supernovae in dispersing elements cannot be overstated. The explosion is a powerful event that effectively seeds the universe with heavy elements, creating a rich chemical diversity necessary for the next generation of stars. As these elements settle into clouds of gas and dust, they may eventually coalesce under the influence of gravity, forming new stars and planets. This cycle of creation and destruction is a fundamental aspect of the universe's evolution. Consider the implications of this process. Every time we look around us, we are surrounded by materials that have traveled through the cosmos, shaped by the fiery hearts of ancient stars. The iron in our blood, the calcium in our bones, and the oxygen we breathe. All of these elements were once part of stellar nucleosynthesis and the subsequent dispersal through supernovae. The universe is a continuous cycle, with each generation of stars contributing to the cosmic tapestry that leads to the formation of life. The understanding of how elements are created and distributed in the universe has been greatly advanced by the work of scientists and astronomers. One such pioneer was Fred Hoyle, who, in the mid-20th century, famously stated, "A supernova is the most energetic event in the universe, and it is the source of the heavy elements we see around us." Hoyle's insights into nucleosynthesis provided a framework for understanding how stars produce the elements essential for life. The study of nucleosynthesis not only deepens our understanding of the universe, but also highlights the intricate connections between different cosmic processes. For example, the formation of elements in stars is closely linked to the life cycle of galaxies. As stars form, live, and die, they enrich their host galaxies with heavier elements, influencing the chemical makeup of future generations of stars. This relationship illustrates the profound interconnectedness of all celestial phenomena. As we explore the universe, we must also consider the varying fates of stars based on their mass. Massive stars, after undergoing nucleosynthesis and experiencing a supernova, leave behind neutron stars or black holes, while less massive stars transform into white dwarfs. Each path contributes uniquely to the cosmic landscape. A neutron star, for instance, is a remnant so dense that a mere teaspoon would weigh as much as a mountain, while black holes represent the ultimate endpoint, regions of space where gravity reigns supreme. This diverse array of stellar outcomes serves to further enrich the universe. The remnants of massive stars, whether they become neutron stars or black holes, influence their surrounding environments, drawing in material and affecting the formation of nearby stars. Imagine the dance of matter swirling around a black hole, spiraling inward, feeding the gravitational beast while simultaneously creating new stars in the surrounding accretion disks. What does this mean for our understanding of the universe's chemical composition? As we analyze light from distant stars and galaxies, we can identify the elements present and trace their origins back to stellar nucleosynthesis. This cosmic detective work allows astronomers to map the abundance of various elements across different regions of the universe and even across cosmic time. By piecing together this information, we gain insights into the processes that shaped our universe from its earliest moments to the present day. In this grand narrative, we find that the universe is not static but rather a dynamic, ever-evolving entity. Each supernova explosion, each new star formation, contributes to a complex web of interactions that shape the cosmos. As elements are recycled through these processes, they foster an environment where the emergence of life becomes a possibility. Imagine the night sky filled with stars, each a beacon of history, each twinkling point of light, a reminder of the cycles of creation and destruction at play. The light we see today is a testament to the stellar processes that have unfolded over billions of years. Each star, a unique story, tells us about the materials that were forged long ago and the paths they took to become part of the fabric of our universe. As we reflect on the implications of stellar nucleosynthesis, we begin to appreciate the profound connections that bind us to the cosmos. The very elements that make up our bodies and our world were born in the hearts of stars, scattered across the universe, and eventually came together to form planets, life, and consciousness. This realization invites us to ponder our place in the universe, a reminder that we are not separate from the cosmos, but rather an integral part of its ongoing story. What a beautiful thought it is to realize that we are stardust, connected to the universe in ways we are only beginning to understand. Each breath we take is infused with the history of the cosmos, as we inhale the remnants of stars that lived and died long before our time. The journey of nucleosynthesis is a testament to the artistry of the universe, a continuous cycle that speaks to the beauty and complexity of existence itself. In this light, we are not merely observers of the universe, we are participants in its grand narrative. Each moment we spend contemplating the stars is a moment spent recognizing the connections that weave through the fabric of reality. As we continue to explore the depths of stellar nucleosynthesis, we uncover not just the origins of elements, but also the deeper truths about our existence and the universe we inhabit. Chapter 9. Star Clusters, Communities of Stars. In the grand expanse of the universe, stars do not exist in isolation. They form communities, coming together in clusters that illuminate the night sky like jewels scattered upon a dark velvet cloth. These star clusters are fascinating celestial entities that can be classified into two primary types: open clusters and globular clusters. Open clusters, like the Pleiades, are young and vibrant, often containing a few dozen to several thousand stars. They typically reside within the arms of spiral galaxies, where the density of gas and dust allows for the continued birth of new stars. Imagine a bustling nursery of celestial bodies, where young stars are born from the same molecular cloud, sharing a common origin. The stars in these clusters are loosely bound by gravity, dancing together in a graceful yet chaotic manner. In contrast, globular clusters present a more ancient and densely packed assembly of stars. These clusters can host hundreds of thousands to millions of stars, all orbiting a common center. Picture a tightly knit family gathering, where every member has their own stories to tell, yet all are bound together by shared history. Globular clusters are typically found in the halo of galaxies, remnants of a time when the universe was younger and more chaotic. They represent some of the oldest objects we can observe, with ages that often exceed 10 billion years. The dynamics and evolution within star clusters reveal a compelling narrative of cosmic interaction. As stars within a cluster age and evolve, they influence one another through gravitational interactions. Imagine the gentle tug-of-war between these celestial bodies, where the gravitational pull of one star can affect the trajectory of another. This interplay can lead to fascinating phenomena, such as the exchange of mass between stars, star collisions, and even the formation of exotic objects like binary star systems. As these clusters evolve, they undergo various stages of life. Open clusters, being younger, may eventually disperse as their stars gain enough velocity to escape the gravitational pull of the cluster. The once tight-knit community becomes a scattering of individual stars, each embarking on its own journey through the cosmos. Globular clusters, on the other hand, face a different fate. Their dense environments foster interactions that can lead to the formation of compact objects, such as neutron stars and black holes. These clusters serve as cosmic laboratories, where the life cycles of stars can be studied in detail. The older stars within globular clusters are often in advanced stages of evolution, allowing astronomers to glean insights into the processes that govern stellar life and death. The significance of star clusters extends far beyond their beautiful formations. They serve as crucial tools for studying stellar evolution. By examining clusters, astronomers can better understand how stars evolve over time, particularly when it comes to their age, composition, and the processes that govern their life cycles. Consider the implications. By studying a globular cluster, scientists can determine the age of its stars by analyzing their color and brightness. The Hertzsprung-Russell diagram, a fundamental tool in astrophysics, allows researchers to plot these stars based on their luminosity and temperature, unveiling their evolutionary stages. In this way, star clusters act as time capsules, preserving the history of stellar evolution. Notable star clusters add to the richness of this narrative. The Orion Nebula, an open cluster, is a prime example of a stellar nursery. It is home to young, hot stars that illuminate the surrounding gas and dust, creating a stunning visual spectacle. Imagine standing at the edge of this nebula, where new stars are born in a cosmic cradle, radiating energy and light as they begin their journeys across the universe. On the other hand, the globular cluster known as M13 in the constellation Hercules showcases the beauty of ancient stellar populations. This densely packed sphere of stars contains some of the oldest known stars, offering a glimpse into the early universe. Imagine witnessing the glowing relics of a bygone era, each star a testament to the dynamic history of our cosmos. Another remarkable cluster is the famous Omega Centauri, the largest globular cluster in our galaxy. It harbors a diverse array of stellar populations and intriguing remnants of stellar evolution, hinting at complex processes that have occurred over billions of years. Its unique characteristics challenge our understanding of how such clusters can form and evolve. As we explore these clusters, we cannot help but wonder how they reflect the broader processes of cosmic evolution. What stories are hidden within their depths? How might they hold the keys to understanding the origins of our own solar system? Star clusters, with their intricate dynamics and rich histories, are invaluable to astronomers seeking to unravel the mysteries of the universe. Each cluster is a chapter in the grand cosmic narrative, revealing insights into the formation and evolution of stars, galaxies, and the universe itself. As we gaze at these celestial communities, we are reminded of our own connections, how we too exist within a web of relationships, influenced by the forces around us. The stars, in their clusters, echo the dance of life, showing us that even in the vastness of space, there is unity and connection. The exploration of these star clusters invites us to reflect on our place in the cosmos, and the journey of discovery continues, unfolding like the stars themselves. Clusters of stars are not just collections of luminous bodies. They are a window into the intricate processes that shape our universe. Within these cosmic communities, we observe not just the stars themselves, but the dynamic interplay of their lives and deaths. The gravitational dance among stars and clusters leads to fascinating phenomena, including the creation of exotic stellar formations. Consider the concept of stellar interactions. In the dense environments of globular clusters, the gravitational influence of one star can lead to the capture of another, resulting in binary or even higher-order star systems. Imagine two stars, once solitary, now bound together in a shared existence, orbiting one another in a celestial embrace. This dance can lead to dramatic outcomes, such as the exchange of mass between stars, where one partner siphons material from the other. Such interactions can ignite new phases of stellar evolution, causing a star to become more luminous, or even triggering a supernova if conditions are right. What happens when these interactions escalate? In some cases, they can lead to stellar collisions. While such events are rare, the impact is profound. When two stars collide, they can create a cascade of energy that results in the formation of a new, more massive star, or even a more exotic object, such as a black hole. The universe, it seems, thrives on change and transformation, constantly reshaping itself through the interactions of its constituents. As we turn our gaze back to the clusters, we can appreciate their role as cosmic laboratories. The study of these clusters allows astronomers to observe the life cycles of stars in various stages of evolution. For instance, the presence of both main sequence stars and red giants within a single cluster provides insight into the age and evolutionary timeline of its members. By analyzing the different types of stars present, scientists can infer not only the age of the cluster, but also the history of star formation within it. The significance of star clusters extends into the realm of cosmology, where they serve as markers of the universe's evolution. When we study globular clusters, we are essentially peering back in time, witnessing the remnants of an earlier epoch in cosmic history. The stars within these clusters are akin to ancient mariners, bearing tales of a universe that was once a tumultuous sea of particles and radiation. One cannot ignore the notable star clusters that dot our night sky, each with its unique characteristics. The Hyades, another open cluster, stands as one of the nearest clusters to Earth. This collection of stars, located in the constellation Taurus, provides a remarkable opportunity for study. The proximity of the Hyades allows astronomers to measure the distances to its stars with unprecedented accuracy, enhancing our understanding of stellar distances and the scale of the universe. In contrast, the globular cluster 47 Tucanae offers a different glimpse into the cosmos. This cluster, teeming with stars, is one of the brightest globular clusters observable from Earth. Here, the study of stellar populations reveals a wealth of information about the processes that govern the formation of stars in dense environments. The intricate balance of gravitational forces and interactions creates a rich tapestry of stellar life that speaks to the complexity of the universe. As we ponder these clusters, we must also consider the role of dark matter in shaping their dynamics. The gravitational forces that bind these clusters together are influenced by unseen matter that permeates the cosmos. Dark matter, which cannot be observed directly, plays a crucial role in the formation and stability of star clusters. It serves as the scaffolding upon which galaxies and their clusters are constructed, creating a gravitational well that enhances star formation and cluster dynamics. What does this mean for our understanding of the universe? The presence of dark matter suggests that the cosmos is far more complex than we can perceive with our senses. It challenges our understanding of gravity and the fundamental forces that govern the motion of celestial bodies. As astronomers continue to unravel the mysteries of dark matter, they gain deeper insights into the nature of star clusters and their evolution. The journey through the cosmos is far from straightforward. Each star cluster embodies unique tales of birth, life, and death, reflecting the broader cosmic narrative. The intricate interrelations among stars, their life cycles, and the forces that shape their destinies weave a complex story that echoes throughout the universe. In our quest to understand these stellar communities, we are reminded of the connections that bind us, both to each other and to the cosmos itself. Just as stars are born from the remnants of their predecessors, we too are shaped by our experiences and relationships, echoing the fundamental truths of the universe. The exploration of star clusters invites us to consider our place within this grand tapestry and to marvel at the intricate web of life that connects all things. Thus, the narrative of star clusters unfolds, rich with the promise of discovery and insight. As we continue our journey through the cosmos, we find ourselves drawn into the stories these clusters tell, eager to learn more about the forces that govern our universe and the connections that define our existence. Throughout the cosmos, the intricacies of star clusters extend beyond mere aesthetics. They are vital to our understanding of the universe's history and future. Each cluster tells a unique tale of cosmic evolution, shaped by the forces that bind its stars together. As we sift through the starlit tapestry of these clusters, we uncover not only the evolution of individual stars, but also the collective behavior that emerges from their interactions. The significance of star clusters in studying stellar evolution is profound. By examining their composition and age, astronomers can piece together the timeline of star formation and the chemical enrichment of the universe. When we gaze at a globular cluster, we observe stars that formed during an era when the universe was still young. These ancient stars are often rich in heavy elements crafted through generations of stellar nucleosynthesis. Imagine the echoes of supernovae reverberating through time, their remnants enriching the interstellar medium from which new stars and planets arise. A particularly notable characteristic of star clusters is their ability to host a variety of stellar types, including main sequence stars, giants, and remnants of stellar evolution. The presence of different stellar populations allows scientists to study the life cycle of stars in real time. For instance, within an open cluster like the Pleiades, one can witness the vibrant youth of stars still in their main sequence phase, juxtaposed against older, more evolved stars. This diversity provides a living laboratory to explore how stars of varying masses and compositions evolve differently. The dynamic interactions within these clusters forge pathways for understanding cosmic phenomena. Consider the role of binary and multiple star systems, which frequently arise in dense star clusters. The gravitational pull between stars can lead to fascinating scenarios, one star siphoning material from another, creating bright, luminous accretion disks, or even leading to cataclysmic events such as novae. Each interaction enriches the tapestry of stellar evolution, revealing the complexities of gravitational dance. Not only do star clusters serve as laboratories for stellar evolution, but they also provide insights into the broader structure of galaxies. As we explore clusters, we gain knowledge about the gravitational forces at play, including the mysterious presence of dark matter that gives clusters their form. This unseen matter influences the motions of stars, shaping the clusters and their fates. The interplay between visible and dark matter challenges our understanding of gravity, urging astronomers to refine their models of the universe. As we consider the vast array of star clusters, we cannot overlook the remarkable individuals who have dedicated their lives to unraveling these mysteries. Notable astronomers such as Henrietta Swan Leavitt made groundbreaking contributions through her study of variable stars within clusters, establishing the foundation for measuring cosmic distances. Her work illuminated the path for future generations, allowing us to understand the scale of the universe in ways that were previously unimaginable. Imagine standing in the shoes of these pioneering scientists, peering into the depths of the cosmos, driven by the desire to comprehend the very fabric of existence. Each discovery within a star cluster is like a breadcrumb, leading us further down the path of knowledge, revealing the interconnectedness of all things. As we reflect on the journey of star clusters, we are reminded of our place within this grand cosmos. Just as stars form communities that share their fates, we too are part of a larger community, woven together by shared experiences and cosmic forces. Each cluster we study resonates with the stories of the universe, inviting us to delve deeper into the profound connections that bind us to the stars. In this exploration of star clusters, we find ourselves not only marveling at their beauty, but also contemplating the intricate processes that govern their existence. The universe, with its boundless mysteries, continues to inspire curiosity and wonder as we seek to understand the very nature of reality. Each star cluster serves as a reminder of the elegance of cosmic design, urging us to embrace the journey of discovery and the connections that define our shared existence. Chapter 10: The Life Cycle of Stars, an Ongoing Cosmic Cycle. The life cycle of stars unfolds as a remarkable journey through various stages, each filled with transformation and rebirth. Stars are born, live out their lives, and ultimately die, only to contribute to the cosmic cycle anew. Imagine this cycle as a celestial rhythm, where each phase resonates with the pulse of the universe, creating a melody that has echoed through the ages. In the beginning, stars emerge from the dense clouds of gas and dust we explored in earlier chapters. The journey starts in the heart of molecular clouds, where gravity pulls particles together, forming protostars. This initial stage is crucial. It is the moment when potential collides with possibility. As protostars continue to gather material, they ignite the fusion process that leads them to the main sequence stage. Here, they become stable, fusing hydrogen into helium and radiating energy across the cosmos. This stable phase can last billions of years, providing light and warmth to the surrounding worlds. However, as stars age, they inevitably exhaust their hydrogen supply. The transition into red giants marks a significant transformation, as the star's core contracts and the outer layers expand. Imagine a gentle balloon swelling until it reaches its limit, then beginning to change shape. This expansion leads to a new ignition of fusion in surrounding layers, creating even heavier elements. The once stable star now becomes a vibrant beacon of change, showcasing the beauty of stellar evolution. As red giants approach the end of their lives, they face their grand finale, a supernova explosion. This climactic event is not merely an end, but a spectacular release of energy that enriches the cosmos with heavy elements, which will eventually form new stars and planets. The interconnectedness of stellar outcomes becomes evident here. The death of one star is the birth of another, a cycle of creation and destruction that shapes the universe. From the remnants of these supernovae, we witness the birth of neutron stars and black holes, each representing different paths based on the mass and conditions of the original star. Neutron stars, with their incredible density, challenge our understanding of matter itself. Their existence raises questions about the nature of gravity and the fundamental forces in the universe. On the other hand, black holes represent the ultimate fate of massive stars, regions where gravity reigns supreme, warping space and time itself. The impact of stellar evolution on the universe is profound. Each stage contributes to the cosmic tapestry, seeding the interstellar medium with essential elements that will foster new star systems. The processes that stars undergo create the very ingredients for life. Carbon, oxygen, and nitrogen, all synthesized in the cores of stars, are the building blocks of planets, and, eventually, life. This continuous cycle emphasizes the interconnectedness of all cosmic entities. As we look to the future, the exploration of stars and their life cycles remains a fertile ground for scientific inquiry. Advancements in technology allow us to peer deeper into the universe than ever before. Observatories equipped with powerful telescopes reveal the birth of new stars in distant galaxies, while missions aimed at understanding the behavior of neutron stars and black holes continue to expand our horizons. The study of gravitational waves, ripples in space-time caused by merging black holes or neutron stars, opens new avenues of exploration, providing insights into the dynamics of these enigmatic objects. Imagine the possibilities that lie ahead. What secrets will the future unveil about the life cycles of stars? How will our understanding of these processes evolve as we gather more data and refine our theories? The universe is a vast, intricate puzzle, and each discovery adds a piece to the collective understanding of our cosmic origins. In essence, the life cycle of stars is not merely a scientific concept. It embodies the profound connection we share with the universe. We are, in many ways, intricately linked to the stars that illuminate our skies. As we reflect on the journey of these celestial bodies, we recognize that their stories are intertwined with our own, reminding us of the beauty and complexity of existence. The ongoing cycle of birth, life, and death among stars invites us to ponder our place in the cosmos and the legacy we leave behind. Each star that flickers in the night sky tells a story of transformation, illuminating the pathways of evolution and creation that shape the universe we inhabit. The interconnectedness of stellar outcomes also presents intriguing possibilities. For instance, the elements created in the cores of stars are dispersed into the universe when a star dies. These elements can later coalesce to form new stars, planets, and even the very life we know. It is a reminder that we are all part of a larger, cyclical narrative, where each chapter of existence is written in the language of stars. As we ponder the future directions in stellar research and exploration, we find ourselves standing on the precipice of discovery. The universe, with its vastness and complexity, continually invites us to question, to explore, and to understand. What new technologies will emerge to deepen our understanding of stellar evolution? How will future generations of astronomers and physicists illuminate the mysteries that still elude us? With every advancement, we inch closer to unraveling the secrets of the cosmos. The life cycle of stars serves as a profound reminder of the beauty of transformation, of the eternal dance of creation and destruction that defines our universe. As we gaze into the night sky, let us carry with us the knowledge that we are part of this grand cosmic cycle, woven into the very fabric of existence by the stars that once burned bright in their own life cycles. As we reflect on the intricate life cycles of stars, we see a rich tapestry of interconnected outcomes that shape not only the cosmos but also the very elements that form our world. Each stage in a star's life is intimately linked to the next, creating a continuum that underscores the dynamic nature of the universe. The death of one star gives rise to the potential for new stellar beginnings. When a massive star explodes as a supernova, it disperses the very elements forged in its core into the vast interstellar medium. This cosmic recycling process is essential. It enriches the gas and dust clouds that will eventually coalesce to form new stars, planets, and perhaps even life itself. Consider the journey of carbon. Initially formed in the hearts of massive stars, it finds its way into the fabric of newly birthed stars and planets, ultimately becoming a fundamental component of life as we know it. This cyclical narrative reminds us of the fragility and resilience of existence. It raises profound questions. What role do we play in this cosmic cycle? How do our own lives echo the processes that govern the stars? The impact of stellar evolution extends far beyond the immediate vicinity of the stars themselves. The elements released during supernovae and the winds from red giants contribute to the composition of galaxies, influencing the formation of solar systems and the conditions necessary for life. The very air we breathe, the water we drink, and the soil that nurtures our plants are all products of this stellar alchemy. The interconnectedness of stellar outcomes illustrates a remarkable truth. We are, in essence, a continuation of the cosmic narrative. As we delve into future directions in stellar research, we find ourselves equipped with ever-evolving tools and technologies that enhance our understanding of the universe. Advanced telescopes, such as space-based observatories, allow astronomers to observe distant galaxies and their star-forming regions in unprecedented detail. By analyzing the light emitted from these celestial bodies, scientists can glean insights into their composition, age, and the processes that govern their evolution. Imagine standing in front of a vast canvas, where each brushstroke represents a different star, each hue a unique story waiting to be told. The ongoing research into the life cycles of stars is akin to learning to read this cosmic artwork. As we uncover the mysteries of stellar formation, we gain a deeper appreciation for the universe's complexity and beauty. The study of gravitational waves has also emerged as a groundbreaking area of research. These ripples in spacetime, generated by catastrophic events such as the collision of neutron stars or black holes, offer a new lens through which to observe and understand the universe. Each detection of gravitational waves opens a new chapter in our understanding of stellar evolution, allowing us to witness the dramatic ends of massive stars from a perspective previously thought unattainable. As we venture further into the cosmos, the potential for discovery remains boundless. The question arises, what other enigmatic phenomena await us? The universe is a treasure trove of secrets, and with every advancement in our observational capabilities, we inch closer to revealing the hidden wonders of stellar life. We stand on the shoulders of giants, scientists and astronomers who have dedicated their lives to unraveling the mysteries of the stars. Figures like Edwin Hubble, whose observations of distant galaxies reshaped our understanding of the universe's expansion, remind us that the quest for knowledge is a shared journey. Their insights have laid the foundation for current explorations, inspiring new generations to look to the skies with wonder and curiosity. The future of stellar research is not solely confined to observations. It also encompasses the development of theoretical models that attempt to explain the intricate processes governing stellar evolution. By simulating the life cycles of stars, scientists can explore various scenarios, providing a framework to understand the myriad ways in which stars form, evolve, and ultimately perish. These models serve as a guide, illuminating the pathways that connect the birth of stars to the formation of galaxies and the universe's large-scale structure. Moreover, the importance of interdisciplinary collaboration in this field cannot be overstated. Astrophysicists, chemists, and planetary scientists are coming together to explore the connections between stellar evolution and the emergence of planetary systems. Their work helps us comprehend how stars, through their life cycles, contribute to the conditions necessary for life. As we ponder the ongoing cosmic cycle, we are invited to embrace our role within it. The stars, with their luminous glow, serve not only as distant beacons but as reminders of our shared origins. The elements that comprise our bodies and the very fabric of our existence were once forged in the hearts of stars. This profound realization beckons us to consider the larger narrative of life itself. Each star that flickers in the night sky carries with it the story of transformation, a whisper of the universe's history. As we gaze upon these celestial bodies, we may find solace in knowing that we are part of this grand cycle, a cosmic tapestry woven from the ashes of stars, interconnected in ways that transcend time and space. In this ongoing exploration of the life cycle of stars, we uncover the intricate threads that bind us to the universe. The beauty of stellar evolution lies not only in the individual stories of stars, but also in the collective narrative they create. Each stage of a star's life resonates through the fabric of the cosmos, echoing the rhythm of creation and destruction that defines our existence. As we continue to explore the universe, we remain open to the myriad possibilities that lie ahead. What new revelations will emerge from our studies of stellar phenomena? How will our understanding of these cosmic